Good evening, ladies and gentlemen. How are you all doing? Can everyone hear me? Okay, cool. So, while seeing you name Mr. Melville, it was good meeting you today and a few other students. It was very good meeting you all. So, Mr. Melville, I have watched your video on Planet Nine and I completely disagree with it. Firstly, there's not enough evidence. So I agree from the guy from UCLA. So it's more psychological thing. So people want to believe that there is a Planet Nine, but it's not enough evidence for Planet Nine. And the guy that's supposed to be the investigating Planet Nine, he has a few mistakes he made. So he said since 2017 they had two good observation stints. That is rubbish. So that means he hasn't spent time at optical observatories. So, for example, take Sutherland, for example, the South African Large Telescope SALT. It is built in a place where you have the best possibility viewing ever. So, with Sutherland, if Sutherland is chosen for a site for observatory because out of your 365 days or nights per year you have in Sutherland, you get 270 nights per year. That is absolute perfect. That means the atmosphere is stable, no water vapor in the atmosphere, no cloud cover. So that's a mistake he made. So I think he's not using the correct equipment, or he doesn't really know how telescopes operate and work. And secondly, with our radio telescopes and our optical telescopes, we have mapped our solar system fairly well. And we know what the gravitational pull and mass of our solar system is. So if there's a gravitational pull in a solar system, we can fairly accurately know what is going on and what it is. So there's not enough evidence for it. Um, but yes, I agree from the guy from UCLA that says it's more psychological thing. So have you heard anything from the faculty about a semester test? I'm just waiting for a reply from the HOD. So hopefully I will get back to you guys tomorrow on it. Pleasure. Then before we begin, do you guys have any questions? I'm also doing well, thank you. So last night we ended off with this slide. So let's continue from here. Oh, before I forget, before starting, I said in last night's class we'll go through the memo of both quizzes. Do you guys want to go through it? Okay, so let's go through the memos of the quiz. So let's share my screen. Can everyone see my screen? So here we can see the first quiz. So the first question is, our Milky Way galaxy has a diameter of 75,000 light years. How long does it take light to cross the diameter of the galaxy? 75,000 years. So, but the quiz is not due yet. So this is the first quiz. Yes, this is how ClickUp looks from my side. So this is the first quiz. So you guys understand why it's 75,000 light years? Everyone happy with question A? Okay, so question B. Is the apparent visual magnitude of a star is 7.3. This tells us the star is what? So if you remember apparent visual magnitude, we can only see until magnitude 6 with our unaided eye. So it's one of the brightest stars in the sky? No, that's it's usually around about -10. So bright enough that it would be visible even during day? No. Not visible with the unaided eye? Yes. Very far from Earth? Not necessarily. Very close to Earth? Not necessarily. So C is the correct answer. Then going to question 3. So most of the light we see coming from the sun originates in A, the chromosphere, B, the photosphere, the corona, the sunspots, or the magnetic field. So no, the photosphere is the visible part of the sun's atmosphere. So therefore the answer is B, the photosphere. Then question number 4, the average distance from Venus to the sun is. So we know the distance from sun to earth is 1 astronomical unit. And Venus is closer to the sun than Earth. So 1.2 light years is way too long. 1.3 million kilometers, that is way too short. 1 billion kilometers, again, that is way too far. 2.3 million miles, that's way too short. But we know Earth to the sun is 1 AU. Venus orbit is close to the sun, so it has to be 0.72 AU. Then last question of the quiz is which star with absolute magnitudes given below has the greatest luminosity? So we know the more negative the number is, the higher the luminosity is. So yeah, the biggest number is -6, and that's why that is the most luminous star. Is everyone happy with these explanations? Awesome, and then you guys want to go through quiz 2 memo? So let's do quiz number 2. It's not due yet, so I still have to do it. Okay, then I won't do quiz number 2 now. Then we will do quiz number 2 next week. Such honest people, yes. You almost, I would have shown you it, but now you tell me the last day to do it is tomorrow. So thank you for being honest. Well, it wasn't quiz. Let me quickly check on my side when the quiz is due. So I'll show you guys. Oh, let me go to the quiz and I will tell you guys when it is due. Yes, so the quiz is still available. So can I ask a question? So why don't you type in the chat so I miss it on the board? Oh, yes, that is why it has two dates. So it's, yes, I checked on my side, it's due tomorrow. But one thing that we have to do is we have to set the due date a little bit further, because sometimes there's a glitch on Blackboard and then they release the memo without it on yet time. So if we set the due date even further, then we are ensuring that the memo is not released. So yes, it is due tomorrow at midnight. The due date is tomorrow midnight. Okay, so is everybody happy with this explanation? Everybody still happy with the work? Okay, so let's begin our lecture for this evening. So now we're going to talk about what happens when this protoplanet clears the nebula. So the sun probably formed along with many other stars in a cloud of interstellar material. You have already learned that observations of young stars suggest that radiation and gravitational effects from nearby stars that have tended to disturb and remove the disk of planet construction material around the sun. Even without those external effects, four internal processes would have gradually destroyed the solar nebula. The most important of these internal processes was radiation pressure. When the sun became a luminous object, light streaming from its photosphere pushed against the particles of the solar nebula. Large bits of matter, like planetesimals and planets, were not affected. But low mass specks of dust and individual atoms and molecules were pushed outwards and eventually driven from the system. The second effect that helped clear the nebula was the solar wind. The flow of ionized hydrogen and other atoms away from the sun's upper atmosphere. So this flow is a steady breeze that rushes past Earth at about 400 kilometers per second. Young stars have even stronger winds in stars of the sun's age, and also irregular fluctuations in luminosity, like those observed in young stars such as the T Tauri stars, which can accelerate the wind. The strong surging wind from a young sun may have helped push dust and gas out of the nebula. The third effect that helped clear the nebula was the sweeping up of space debris by the planets. All of the old solid surfaces in the solar system are heavily cratered by meteorite impacts. Earth's moon, Mercury, Venus, Mars, and most of the moons in the solar system are covered with craters. A few of these craters have been formed recently by the steady rain of meteorites that falls on all the planets in the solar system. But most of the craters appear to have been formed before roughly 4 billion years ago in what is called the heavy bombardment, as the last of the debris in a solar nebula was swept up by the planets. So, a good question for the test and exam is, I can ask you what these four stages are. So here we can see every old solid surface in a solar system is scared by craters. So in image A, we can see Earth, Moon have craters ranging from basins hundreds of kilometers diameter down to microscopic bits. And in image B, the surface of Mercury, as photographed by passing spacecraft, shows vast numbers of overlapping craters. The fourth effect was the ejection of material from the solar system by close encounters with planets. If a small object such as a planetesimal passes close to a planet, the small object's path will be affected by the planet's gravitational field. In some cases, the small object can gain energy from planet's motion and be thrown out of the solar system. Ejection is most probable in encounters with massive planets. So the Jovian planets were probably very efficient at ejecting the icy planetesimals that formed in the region of the nebula. Attacked by the radiation and gravity of nearby stars and cracked by internal processes, the solar nebula could not survive very long. Once the gas and dust were gone and most of the planetesimals were swept up, the planets could no longer gain significant mass, and the era of planet building ended. So are there any other planetary systems? The evidence says yes. Do they contain planets like Earth? The first such objects have now been discovered. So do you guys can guess what telescope this is? And how these planets were discovered? No, this is not the X-ray space telescope Chandra. Yeah, you're right. It looks like an exhaust. This telescope was built for a specific aim. This is the Kepler Space Telescope, and the Kepler Space Telescope is our planet hunter. So this telescope was specifically designed and to search for other planets. And it is still operating today. I'm speaking under correction, but a last. So yes, this telescope can be used to search for Planet 9, Mr. Melville, yes. So that is why there's another contradictory evidence that Planet 9 does not exist. Because this telescope can find planets in other star systems, but it can't find Planet 9, so Planet 9 can't exist. So the Kepler telescope, if I'm speaking under correction, the last time I checked, it found something like 200,000 other planets. And from the 200,000 planets being discovered, roughly about 2,000 of them is in the habitable zone around the host star, which may contain life. So that is interesting. Can anyone tell me how Kepler discovers these exoplanets? So what are you saying, Mr. Marvel? Well, exoplanets are discovered by the dipping of the light, but Planet 9 won't do that. Yes, so does anyone so Mr. Hennen, doesn't it use transits of planets? Yes, you guys are correct. So what happens? Yeah, so let me get the whiteboard out. How Kepler does it. So where's the whiteboard? So let's say this is the host star, and this is a planet orbiting the star. So Kepler will look at the light coming from that star, and then it will wait until that planet transits in front of the star. That's meaning moving in front of the star. That means we will be able to see a little dot moving across the surface of that star, and we will see the total brightness of that star dip as well. That means there's a planet transiting that star. That's the easiest way to detect if a planet is around that host star. And so we go back to, so let's go back to our slides. Okay, so yeah, the stars, here's our, what if it's a smaller companion star? So yes, that is one thing we can determine, but so it's a smaller companion star. That is why I'm coming to the next point. So if we found a transit, the next thing we do is we look at the spectrum of that object. So remember, as we learned of Kirchhoff laws, we now have a warm continuous background and we look through the atmosphere. So that means we get we get an emission spectrum from that object. And therefore we know what its composition is. So therefore we can determine if it is a host star or planet moving in front. The host or companion star will be a lot bigger. But that is one way we can determine what the composition of that host planet is. So if that host planet has an atmospheric composition that contains oxygen, nitrogen, carbon dioxide, we know it might be Earth-like. So the solar system that the Kepler telescope discovered that is almost exactly or most comparable to Earth is the Kepler 22 system. So around every star, depending on the size of the star, the temperature and luminosity of the star, there is a patch called the habitable zone. I don't like that word. I like to call it the Goldilocks zone. So think of the Three Little Bears and Goldilocks. The porridge, it's not too cold, it's not too warm, it's just right. That's the same analogy with the Goldilocks zone around the planet. It's not too cold, it's not too warm, it's just right. So to support life on a host planet. So if we try to determine if there is a planet that might host other life, we first look, is that planet orbiting in the habitable zone or the Goldilocks zone around that planet? And then we look at the spectrum of that planet. And if that spectrum is similar to Earth's, we flag that. And here we can see Kepler 22b is it's in the Kepler 22 system. So it is a planet around a host star that's in the habitable zone, and it has more or less the same composition as Earth. So that is one planet that is extremely, extremely interesting to monitor. But something interesting else, the Kepler telescope discovered as well is the Kepler 62 system. So in its habitable zone, there are actually two planets, Kepler 62f and Kepler 62e, that forms in the Goldilocks zone. And closer to its orbit, there are three other planets as well. So looking at Earth, here we have two planets in the habitable zone. We have Earth and Mars, and here we have other planets orbiting closer to the host star as well. So that is something really, really cool. And that is what Kepler Space Telescope is doing and what exoplanet scientists is looking for. So both visible and radio wavelength observations detect dense disks of gas and dust orbiting young stars. For example, at least 50% of the stars in the Orion Nebula are surrounded by such disks. A young star is detectable at the center of most disks, and astronomers can measure that the disks contain many Earth masses of material in a region a few times larger in diameter than our solar system. The Orion star-forming region is only a few million years old, so planets have not formed in these disks yet. Furthermore, the intense radiation from the nearby hot stars is evaporating the disk so quickly that planets may never have a chance to grow large. The important point for you to consider is that so many young stars have disks. Evidently, disks of gas and dust are a common feature around stars that are forming. The Hubble Space Telescope also can detect dense disks around young stellar stars in another way. Some disks show up in silhouette against the nebula that surround the newborn stars. These disks are related to the formation of bipolar flows in that they focus the gas flowing away from a young star into two jets shooting in opposite directions. So here we can see in this image, we can see dark bands, so indicated by arrows, are edged on disks of gas and dust around young stars seen in Hubble Space Telescope near-infrared images. Planets may eventually form in these disks. These systems are so young that material is still falling inward and being illuminated by light from the stars. So something that just came to mind now seeing these images. So on campus today, I had a discussion with one of my other colleagues, Dr. Sion Basu. He and Professor Roger Dean is working on a few projects. So I think on the 12th or the 13th, the EHT, Event Horizon Telescope, is going to make a new announcement and have scheduled a press release. So we are sure they are going to release the image of the center of our galaxy. So that meaning the supermassive black hole in the center of our own galaxy. So that will be a cool announcement that you guys can follow on YouTube as well. In addition to these dense hot disks forming planets around young stars, infrared astronomers have found cold, low-density dust disks around stars much older than the newborn stars in Orion. Old enough to have finished forming, these tenuous dust disks are sometimes called debris disks because they are evidently made of dusty debris produced in collisions among small bodies orbiting those stars that resemble asteroids, comets, and Kuiper Belt objects in our solar system, rather than this just left over from the original protostellar disk. That conclusion is based on calculations showing that the observed dust would be removed by radiation pressure in a much shorter time than the ages of those stars, meaning the dust there now must have been created relatively recently. Our own solar system contains such second-generation dust produced by asteroids, comets, and Kuiper Belt objects. Astronomers consider the solar system's Kuiper Belt extending beyond the orbit of Neptune as an example of cold debris disks. So just a heads up to everyone. So my load shedding is scheduled for 6. So if I disappear in the next 5 to 10 minutes, just bear with me while I reconnect. Some examples of debris disks around the stars, Beta Pictoris and Epsilon Eridani, is in figure 15.12 that we're going to look at now. So the disk around Beta Pictoris, an A-type star, more massive and luminous than the Sun, is about 20 times the diameter of our solar system. The dust disk around Epsilon Eridani, which is a K-type star, somewhat smaller than the Sun, is similar in size to the solar system's Kuiper Belt. Like most of the other known low-density disks, both of these examples have central zones with even lower density. Those inner regions are understood to be places where planets have finished forming and have swept up most of the construction material. In fact, both Beta Pictoris and Epsilon Eridani are now known to have planets. So here we can see in image A, the disks have been detected orbiting a number of stars. But in visible part of the spectrum, the dust is factors of 10 to the power 2 or to 10 to the power 3 times fainter than the stars, which must be hidden behind masks to produce the dust detectable. The second faint inclined disks in the Beta Pictoris system shows the orbital plane of a massive planet. So in image B, we can see at far infrared wavelengths, the dust in the debris disk is generally much brighter than a central star. Warps and clumps in these disks can indicate the gravitational influence of planets. So note that this is the same system portrayed in the opening of this chapter. Infrared observations reveal that famous star Vega, easily visible in the northern hemisphere summer sky, also has a debris disk. And detailed studies show that most of the dust particles in that disk are tiny. Radiation pressure from Vega should blow away small dust particles quickly. So astronomers conclude that the dust being observed now must have been produced by a big event, like the collision of two large planetesimals within the last million years. Fragments from the collision are still smashing into each other now and then producing more dust, continuing to enhance the debris disk. This effect has also been found in disks around other mature stars. Such smash-ups probably happen rarely in a dust disk, but when they happen, they make the disk very easy to detect. So in image A, collisions between asteroids are rare events, but they generate lots of dust and huge numbers of fragments. As in this artist's conception, further collisions between fragments can continue to produce dust, but such dust is blown away quickly. Astronomers treat the presence of dust as evidence that objects of at least planetesimal size must be present. Then in image B, artist's conception of a heavy bombardment episode in young planetary system around the star Eta Corvi. Evidence for this barrage comes from spectroscopic observations by the Spitzer Space Telescope that detected collision fragments of both rocky and icy bodies containing organic compounds. So notice the difference between the two kinds of planet-related disks that astronomers have found. The low-density dust disks, such as the ones around Beta Pictoris and Epsilon Eridani and Vega, are produced by the dust from collisions between remnant planetesimals. Such disks are evidence that planetary systems have already formed. In comparison, the dense disks of gas and dust, such as those seen around the stars in Orion, are sites where planets could be forming right now. A planet orbiting another star is called an extrasolar planet, or in short, an exoplanet. Such a planet would be quite faint and difficult to see so close to the glare of its star. But there are ways to find these planets. To understand one important way, all you have to do is imagine walking a dog. You will remember that Earth and the Moon orbit around their common center of mass, and two stars in a binary system orbit around their center of mass. When a planet orbits a star, the star moves very slightly as it orbits the center of mass of the planet-star system. Think of someone walking a poorly trained dog on a leash. The dog runs around pulling on the leash, and even if it were an invisible dog, you could plot its path by watching how its owner was jerked back and forth. Astronomers can detect a planet orbiting another star by watching how the star moves as the planet tugs on it. And that Mr. Melville is another supporting evidence why Planet 9 can't exist, because we can't see Planet 9 tugging on our own star and our own star tugging on Planet 9. The first planet detected this way was discovered in 1995, orbiting the Sun-like star 51 Pegasi. As the planet circles the star wobbles slightly, and that very small motion of the star is detectable by Doppler shifts in the star's spectrum. From the motion of the star and estimates of the star's mass, astronomers deduced that a planet has at least half the mass of Jupiter and orbits at 0.05 AU from the star. Half the mass of Jupiter amounts to 160 Earth masses, so this is a large planet. Note also that it orbits very closely to its star, much closer than Mercury orbits around our Sun. Yes, Mr. Melville, so very far away the inverse squared law accounts, but even if it's very small, we will still see them tugging on each other. So that's why I said we know exactly what's happening with the gravitational fields in our solar system. So here we can see how this is happening. So can everyone still hear me? Sorry about that. That's load shedding on my side, so I have reconnected. So, Mr. Melville, I saw you said yes, you can see the tug of asteroids, but remember, asteroids are tugging on each other as well. And through that tugging, we can calculate where the asteroids are and the size of those asteroids. So there's again counter examples and proof that Planet 9 does not exist. So in image A, we can see a person walking a lively dog is stalked off course by the dog. Then image B, the star 51 Pegasi is pulled back and forth by the gravity of the planet that orbits it every 4.2 days. The wobble is detectable in precision observations of the Doppler shifts. Then in image C, a person walking multiple dogs has a complicated motion. Then in image D, Doppler shifts of the star Upsilon Andromeda showed that the combined effects of at least 4 planets orbiting it. The influence of its shortest period planet has been removed in its graph to reveal more clearly the orbital influence of the other 3 planets. We don't see asteroids only on one side of the solar system. We see asteroids around the entire solar system. That's why we have an asteroid belt. That's why we have a Kuiper belt, and that's why we have an Oort cloud. So the asteroid's not focused to one side of the solar system. It is spread around the asteroid belt. Astronomers were not surprised by the announcement that a planet had been found orbiting a sun-like star. For years, astronomers had assumed that many stars had planets. Nevertheless, they carefully tested the data and made further observations that confirmed the discovery. In fact, as of this writing, more than 3,000 extrasolar planets have been found by a variety of methods, including at least 7 planets orbiting the star HD 10180, 6 around Gliese 581, and 6 around Kepler 11, true planetary systems. Almost 600 such multiple planet systems have been found so far. Another way to search for planets is to look for changes in the brightness of the star when the orbiting planet crosses in front of a star called a transit. The decrease in light during a planet transit is very small, but it is detectable, and astronomers have used this technique to find many planets. From the amount of light lost, astronomers can tell that these planets with Jovian masses have Jovian diameters and thus Jovian densities and compositions. The Spitzer Space Telescope has detected infrared radiation from two large hot planets already known from star wobble Doppler shifts. As these planets orbit their parent stars, the amount of infrared radiation from each system varies. When the planets pass behind their parent stars, the total infrared brightness of the systems noticeably decreases. These measurements confirm the existence of the planets and indicate their temperatures and sizes. Notice how the techniques used to detect these planets resemble the techniques how to study binary stars. Most of the planets were discovered using the same observational methods used to study spectroscopic binary systems, but some were found by observing the systems as eclipsing binaries. In contrast, a few extrasolar planets have been found by a technique called microlensing, in which an extrasolar planet passes precisely between Earth and a background star, briefly magnifying the distant star's brightness by gravitational lensing. So, Mr. Mavel, even if it is 300 AU past Pluto, we should be able to detect its gravitational influence on the solar system and our own star. And we should still be able to see it with the Kepler Space Telescope and other telescopes as well. Because lower mass planets are longer period planets, are harder to detect, the planets discovered so far tend to be massive and have short orbital periods. Low mass planets don't tug on their stars very much, and present-day spectrographs can't detect the very small velocity changes that these gentle tugs produce. Planets with longer periods are harder to detect because astronomers have not been making high-precision observations for a long enough time. Jupiter takes 11 years to circle the Sun once, so it will take years for astronomers to see the longer period wobbles produced by planets lying further from the stars. You should not be surprised that the first planets discovered are massive and have short orbital periods. The new planets seem puzzling for several reasons. As you have learned from our solar system, the large planets formed further from the Sun, where the solar nebula was colder and ices could condense. How could big planets near their stars, called hot Jupiters, have formed? Theoretical calculations indicate that planets forming in an especially dense disk of matter could spiral inward as they sweep up gas and planetesimals. That means that it is possible for a few planets to become that massive, short-period planets that are detected most easily. Another puzzle is that many of the newly discovered extrasolar planets have eccentric orbits, and a few others appear to have orbits inclined at large angles to the equators of their parent stars. A simple interpretation of the solar nebula theory would predict that planets generally should have nearly circular orbits that lie approximately in their stars' equatorial planes, as do the planets in our solar system. Theorists point out, however, that planets in some young planetary systems can interact with each other or with binary stellar companions and be thrown into eccentric or highly inclined orbits. This effect is probably rare in planetary systems, but astronomers have found some of these extreme systems more easily because they have easily detected wobbles. You might be wondering if astronomers have been able to make images of any extrasolar planets. Getting an image of a planet orbiting another star is about as easy as photographing a bug crawling on the light bulb of a searching light miles away. Planets are small and dim and get lost in the glare of the stars they orbit. Nevertheless, astronomers managed to image a planet orbiting at the inner edge of the debris disk around the star Fomalhaut. Using the Hubble Space Telescope's near-infrared camera, and around the star Beta Pictoris using a specially designed near-infrared camera plus adaptive optics on the Gemini telescope atop Mauna Kea in Hawaii. Both of those discoveries further confirmed the predicted connection between the debris disks and the finished planetary systems. So here in image A, images of Jovian-sized planets orbiting about 120 AU star formaldehyde at the inside edge of the star's previous known debris disk and ring. The inset shows motion of the objects between 2004 and 2012 at the correct rate for a planet at that position orbiting a star of that mass. Then in image B, image of a Jovian-sized planet orbiting 9 AU from the star Beta Pictoris. In both images, the central circle, blank region, represents a combination of hardware and software masks implemented to block light from the central stars that are much brighter than the planets. So here we can see the planet moving along its orbit over here, and here we can see the planet orbiting. The Kepler Space Telescope, launched into solar orbit in 2009, searched for planets by the transit method mentioned in the previous section. Kepler's 42 visual wavelength charge coupled via CCD detectors, so remember in a previous chapter we have discussed CCDs, monitored the brightness of 150,000 solar-type stars during its 4-year primary mission, detected slight decreases in brightness caused by planets passing in front of some of those stars. Kepler's original search field between the constellations Cygnus and Lyra was chosen to be close to, but not in the plane of the Milky Way, so that the number of solar-type stars was maximized relative to other type stars. 2 mouse pointers? What do you mean 2 mouse pointers? As you know, the Sun's diameter is about 100 times larger than Earth's. Therefore, when an Earth-sized planet transits its planet star, meaning moves between you and a star, the planet covers up 1 in 10,000 of the surface area of the star, causing a decrease of 1 part in 10,000. So 1 in 100% in a star's brightness. So remarkably, Kepler's detectors are sensitive and stable enough to detect transits that small. However, only a few % of planetary systems can be expected to have orbits inclined parallel enough to our line of sight so that the transits can be observed. That is the main reason why the target star sample was so large. In this image, we can see the transit light curve of the first confirmed extrasolar terrestrial planet, so Kepler 10b. The planet has an orbital period of 0.84 days. The depth of the transit dip indicates that the planet has 1.4 times the diameter of Earth. Spectroscopic measurements with ground-based telescopes of that parent star, radial velocity variation, give a mass of the planet of 4.6 times Earth mass. The planet's diameter and mass yield a density of 8.8 grams per cubic centimeter, higher than Earth's, indicating a mostly metallic composition. The Kepler search scheme involved very precisely measuring the brightness of each of the 150,000 target stars at least once every 30 minutes, producing a tremendous amount of data that had to be carefully analyzed. The Kepler team was especially interested in finding Earth-like planets, meaning planets that are not only about the size of Earth, but also of Earth-like temperatures. Earth-like temperatures require an orbit of about 1 AU in radius of the parent star, has about the same mass and luminosity as our own Sun. You can see that an Earth-like planet around a Sun-like star will produce a transit only once per year. Each transit will last only 13 hours if the planet's orbit is exactly parallel to the line of sight, and even less time if the orbit is inclined. The Kepler investigators had the amazingly tough task of searching in their data for occasions where some of their 150,000 target stars, nobody knew ahead of time which ones, became 0.01% dimmer than usual for a few hours once per year. And to be sure that the transits actually represented orbiting planets, at least 3 transits spaced equally in that time had to be observed. Unless transits repeated on schedule, any observed variations in the star's brightness could have been caused by other phenomena. Thus, the Kepler investigators required at least 3 years of observations to discover and confirm each Earth-like planet. Of course, finding and confirming planets orbiting closer than 1 AU to their parent star with orbital period shorter than 1 year is quicker. Also, you can see that finding planets in Earth will be easier because they will cover a large fraction of their parent star during transit, causing a more noticeable dip in the light curve. Thus, Kepler easily found many hot Jupiters within a few weeks of the start of the mission. After 4 years of observations and another year of data processing, the total number of confirmed extrasolar planets discovered by the Kepler mission reached more than 2,000, with thousands more candidates waiting for confirmation. The majority of those planets are hot Jupiters or hot Neptunes, larger than Earth, but smaller than Jupiter. About 150 of them are hot Earths. One star designated Kepler-11 has 6 planets, all somewhat larger than Earth, all orbiting closer to the parent star than Venus does to the Sun. Interestingly, because the Kepler-11 planets perturbed each other gravitationally, making successive transits come a tiny bit earlier or later than would happen if they were orbiting alone. Their masses can be estimated. The amount of light lost during the transits gives the diameter of the planets. And you know that combining the masses and diameters lets you calculate the densities. All 6 of Kepler-11's known planets turn out to have densities like Earth or higher. Thus, they are definitely terrestrial planets. So artist conception, comparing the Kepler-11 planetary system with our solar system from a tilted perspective, showing that in both systems, the orbits of the planets lie in single planes. So let's see what you are typing, Mr. Nabel. Planet 9 could even be a black hole the size of a grapefruit, so that's why it could be so hard to observe. There should be a black hole theoretically that close to our solar system, or could just be passing by. I'm not too sure about that. But it could be, but I'm not too sure about that. A few of the extrasolar planets and planet candidates identified by Kepler have transit light curves indicating that they are smaller than Earth in diameter. A handful of these systems have masses determined directly by radial velocity Doppler shift measurements. So far, 8 extrasolar planets orbiting main sequence stars are known to be less massive than Earth. These are all hot Earths, in orbit so close to their parent stars that their surfaces are probably molten rock and metal. So know that several other objects known to have smaller masses than Earth have been found orbiting pulsars, and you can see that in chapter 11. In 2014, the Kepler team announced confirmation of discovery of the first known Earth-sized, Earth-temperature extrasolar planet, designated Kepler 186f. That planet orbits an M-dwarf star with 4 other planets previously discovered by Kepler. You can expect that space observatories will someday be able to image even terrestrial planets directly around sun-like stars. The discovery of extrasolar planets gives astronomers added confidence in the solar nebula theory. The theory predicts that the planets are common and astronomers are finding them orbiting many stars. So I'd bet almost anything that life from another planet, if formed independently from life on Earth, will be more different from all species of Earth life than any 2 species of Earth life are from each other. And that, ladies and gentlemen, was our intro lecture to the different planets. Do you have any questions? So while I'm uploading the next set of lecture slides, let's take a short minute break and we will continue at 6:30. Okay, so let's see, Mr. Melville. So there should be a black hole the distance from Neptune to Pluto, away from Pluto. Read it a while ago, so I don't remember the exact figure, but yeah, the density of black hole and Milky Way is quite high. So yes, that could be, but again, we don't have sufficient evidence to make that claim. So yes, that is another theory. Okay, is everyone back? Cool. Does anyone have questions about the previous lecture slides? So now we understand how planets are formed and how planets are detected. But for us to continue our discussion, we first now need to look at Earth and Moon, and we're going to use that as a basis to compare it to the other planets and moons in our own solar system. So besides being in our solar system, what can you tell me about our Earth and Moon system? Anything you guys can tell me about the Earth Moon system? Yes, tidal locking. So from this lecture and lecture slides, so they are quite far away from each other, that is true. We're going to use them as a travel guide to the terrestrial planets and to understand the terrestrial planets. We're going to look at planet Earth and we're going to look at the moon. And then we're also going to learn what makes Earth quite a special place in our solar system. So, can you guys guess when this image was taken and what this image is about? Not 1964. Yes, this is from the Apollo missions, 1969, Neil Armstrong. But can you guys guess where this image was, who received this image first? This image was received by the Hartebeesthoek site in 1969, where it was originally built. So this image was downloaded here in South Africa from the Apollo mission and then forwarded to Houston, Texas Mission Control. So this picture was taken by the telescope we have here in Hartebeesthoek. And what is interesting about this picture, you can see this picture, it looks like there's a dark line. So that's stitched together vertically. And that is how this image was sent. It was sent bit by bit. So each one of these streaks is a bit of data that is sent to Earth, so to Hartebeesthoek, where everything was stitched back together bit by bit. And that's why it looks like this image was stitched together, but it was actually sent bit by bit by bit. And that is really cool. So this was done and received first in South Africa and then sent to NASA. What's actually very cool about the story is he was the first director of HARDRAIL. The guy's still living, Dr. George Nicholson. I think he is turning 87 or 88 this year. He is still working for the observatory. He was supposed to retire, but he hasn't retired, so he's still continuing. And he said when he started at the observatory, is when he finished his studies and he started his research career. So he said it was his first research posting at the observatory. And he remembers standing outside with the telescope and antenna looking towards the moon, and there are actually people walking on the moon. He was at the Hartebeesthoek site, and that is one of his amazing memories about the site. Standing outside, looking at the moon, looking at equipment pointing towards the moon, and realizing we are doing tracking and telemetry on the Apollo spacecraft. And do you guys recognize this picture? You know what this picture is called? Yes, Mr. Marvel, you are correct. This picture is known as Earth rising. So I'm not exactly sure which Apollo mission was it. This picture was taken from the surface of the moon. And here you can see Earth. So in the preceding chapter, you learned how our solar system formed as a byproduct of the formation of the sun. You also saw how distance from the sun determined the gravitational composition of each planet. In this chapter, you begin your study of the individual planets by comparing and contrasting Earth with its moon. So on the way, you will answer these four important questions. So, number one, how do the Earth and its moon compare with the other terrestrial worlds? Secondly, how has Earth changed and evolved since it formed? Thirdly, why is the moon airless, heavy cratered, and geologically inactive? And then lastly, how are the histories of Earth and the Moon connected? So if you say, Mr. Melville, I don't know how I know all this stuff. You pick it up depending on what you read and what you're listening to. Planets are more alike than they are different. They are described by the same basic principles. You can compare and contrast them to identify those principles and understand planets better. This approach is called comparative planetology. You can learn much more that way than by studying the planets separately. Earth and its moon are ideal starting points for your study because they are respectively the largest and the smallest of the five terrestrial worlds. Earth is a complex planet with a molten interior that generates magnetic field. Its crust is active, with moving continents, earthquakes, volcanoes, and ongoing mountain building. Earth's oxygen-rich atmosphere and water-covered surface are unique in the solar system. In contrast, the Moon is geologically inactive and has no atmosphere. Nevertheless, the histories of Earth and the Moon are intertwined. You will meet the other three terrestrial worlds, Mercury, Venus, and Mars, in the next chapter, and find that many of their properties fit between the benchmarks set by Earth and the Moon. If you visit the city of Granada in Spain, you will probably consult a travel guide. If it is a good guide, it will do more than tell you where to find the museums and restrooms. It will give you a preview of what to expect. You are beginning a journey to the Earth-like world, so you should consult a travel guide and see what is in store. In this chapter and the next, you will visit Earth's moon, Mercury, Venus, and Mars. It might surprise you that the moon is included in your itinerary. It is, after all, just a natural satellite orbiting Earth and isn't one of the planets. But the moon is a fascinating world of its own. It makes a striking comparison with the other worlds on your list, and its history gives you important information about the history of Earth and the other planets. In figure 16.1 compares the five worlds. The first feature you might notice is diameter. The moon is small and Mercury is not much bigger. Earth and Venus are large and quite similar in size, but Mars is a medium-sized world. You will discover that size is a critical factor in determining a world's personality. Small worlds tend to be geologically inactive, while larger worlds tend to be active. In figure 16.1, we can see the planets in comparison. Earth and Venus are similar in size, but the atmospheres and surfaces are very different. The Moon and Mercury are much smaller, and Mars is intermediate size. The terrestrial worlds are made up of rock and metal. Planetary scientists have evidence that they are all differentiated, which means each world is separated into layers of different density, with a dense metallic core surrounded by a less dense rocky mantle and a low density crust on the outside. As you learn in chapter 15, when the planets formed, their surfaces were subjected to heavy bombardment by leftover planetesimals and other debris in the young solar system. You will see lots of craters on these worlds, especially on Mercury and the Moon, many of them dating back to the heavy bombardment era. Notice that cratered surfaces are old. For example, if a lava flow covered up some cratered landscape after the end of the heavy bombardment, few craters could be formed later on that surface because most of the debris in the solar system was gone. When you see a smooth plane on a planet, you can be sure that the surface is younger than relatively heavy cratered areas. Another important way you can study a planet is by following the energy flow. In the preceding chapter, you learned that the heat in the interior of a planet may be partially from radioactive decay and partly left over from a planet's formation. But in any case, it must flow outward towards the cooler surface when it is radiated into space. In the process of flowing outward, the heat can cause convection currents in the liquid interior, magnetic fields, plate motions, quakes, faults, volcanism, mountain building, and more. Heat flowing outward through the cooler crust makes a large world like Earth geologically active. In contrast, the Moon and Mercury, both small worlds, cooled quickly inside, so they have little heat flowing outward now and are relatively inactive. When you look at Mercury and the Moon in figure 16.1, you can see their craters, plains and mountains clearly. Neither has substantial atmosphere to obscure your view. In comparison, the surface of Venus is completely hidden by a cloudy atmosphere even thicker than Earth's. Mars, the medium-sized planet, has a relatively thin atmosphere. You might ponder two questions. First, why do some worlds have atmospheres while some do not? You will discover that both size and temperature are important. The second question is more complex. Where do those atmospheres come from? To answer that question in later chapters, you will have to understand the histories of these worlds. Like the other terrestrial planets, Earth formed from the inner solar nebula about 4.6 billion years ago. Even as it took form, it began to change. There is evidence that Earth and other terrestrial planets, plus Earth's moon, passed through the four developmental stages. So, a hint for you guys, this is a good question for the test or exam. I can ask you, what are the four stages? I can perhaps also ask you to describe the four stages. So the first one is differentiation. That produces a dense core, thick mantle, and low density crust. So that means everything is now moving in different layers. Then secondly, the young Earth was heavily bombarded in the debris-filled early in the solar system, so that's the bombardment phase. Third is flooding by molten rock and later by water can fold lowlands, so third one is flooding. Then lastly, and a fourth one, slow surface evolution continues due to geological processes, including erosion, so slow surface evolution. Everybody happy with that explanation, understanding it? Okay. The first stage of planetary evolution is differentiation, the separation of material into layers according to density. In the next section, you will learn about evidence that Earth is differentiated, with a dense core plus a less dense mantle and crust. That differentiation is understood to have occurred due to melting of Earth's interior caused by heat from a combination of radioactive decay plus energy. Energy released by infalling matter during its formation. Once the interior of Earth melted, the densest materials were able to sink to the core. The second stage, cratering, could not begin until a solid surface formed. The heavy bombardment of the early solar system made craters on Earth just as it did on the Moon and other planets. As the debris in the young solar system cleared away, the rate of cratering impacts decreased towards its present low rate. The first stage of planetary evolution is differentiation, the separation of material into craterings. Is this the same slide as the previous one? Yes, it is. I accidentally copied the slides. The third stage, flooding, began as radioactive decay continued to heat Earth's interior and caused rock to melt in the upper mantle, where the pressure was lower than in the deep interior. Some of that molten rock welled up through cracks in the crust and flooded the deeper impact basins. Later, as the environment cooled, water fell as rain and flooded the basins to form the first oceans. Note that on Earth, basins flooding was first by lava and later by water. The fourth stage, slow surface evolution, has continued for at least the past 3.5 billion years. Earth's surface is constantly changing as sections of crust slide over and against each other, pushing up mountains and shift continents. In addition, moving air and water erode the surface and wear away geological features. Almost all traces of the first billion years of Earth's history have been destroyed by the active crust and erosion. Terrestrial planets pass through these four stages, but differences in mass, temperature, and composition among the planets can enhance some of those stages relative to the other stages and produce surprisingly different worlds. Earth is a good standard for comparative planetology. Every major process on any rocky world in our solar system is represented in some form on Earth. Nevertheless, Earth is unusual among the planets in our solar system in several ways. More than 70% of Earth's surface is covered by liquid water. No other planet in our solar system has liquid water on its surface, although, as you will learn later in chapters, Mars had surface water long ago. Venus probably did, and some moons on the outer solar system show evidence of having liquid water under their surfaces. Your own planet is special in a second way. Some of the matter on the surface of this world is alive, and a small part of that living matter, including you, is aware. As you will learn in chapter 20, life currently seems to be absent from other worlds in the solar system. No one is sure about all the ways that the presence of living matter has affected the evolution of Earth. But as you will learn later in this chapter, the thinking part of the life on Earth, humankind, is actively altering our planet. You have read that there is evidence Earth is differentiated into a dense metallic core with a lower density rock mantle and crust. What is the evidence? A very simple argument is based on the fact that Earth's average density, which can be calculated easily from its mass and volume, is 5.5 grams per cubic centimeter. But the silicate rocks on Earth's surface have only about half that density. Therefore, a large part of Earth's interior must be made of material much denser than crustal rock. Can more detailed information be determined about Earth's interior? Although even the deepest mines and wells extend only a few kilometers down and don't even reach the bottom of the crust, exploration of Earth's interior is possible because earthquakes produce vibrations called seismic waves that travel through the crust, and interior eventually registers on sensitive detectors called seismographs all over the world. Two kinds of seismic waves are important in this explanation. Pressure waves, or P waves, travel as a series of compressions and uncompressions, like sound, and can pass through a liquid. In contrast, the shear waves, or S waves, travel as a type of side-to-side vibration that can't pass through a liquid. When an earthquake occurs, no direct S waves pass through the core to register on seismographs on the opposite side of Earth, as if the core were casting a shadow. The absence of S waves showed that the core is mostly liquid, and the size of the S wave shadow shows that the outer boundary of the core lies slightly more than halfway between Earth's center and its surface. So here in this image, we can see P waves and S waves gives you clues to the structure of Earth's interior. No direct S waves from an earthquake reach the side of Earth opposite their source, indicating that Earth's core is liquid. The size of the S wave shadow tells you the size of the liquid outer part of its core. So here we can see in this S wave shadow, red, only P waves can be detected. And here, as an earthquake sends seismic waves through Earth's interior, so P waves can travel through the core, but S waves travel around the surface. Does everyone understand that? Okay, so let's continue. The P and S waves caused by an earthquake do not travel in straight lines or at constant speed within Earth. The waves may reflect off boundaries between layers of different density, or they may be refracted as they pass through a boundary, and their speed is greater in regions of high temperature and density. Geoscientists can use the arrival times of reflected and refracted seismic waves from different earthquakes to construct a detailed model of Earth's interior. Such studies confirm the interior consists of three parts: a central core, a thick mantle, and a thin crust. Mathematical models based on seismic data indicate that the core is hot, about 6,000 Kelvin, dense, about 13 grams per cubic centimeter, and composed of iron and nickel. The core of Earth is as hot as the gases at the sun's surface, but high pressure keeps the metal solid near the center of the core and liquid in its outer part. Earth's magnetism gives you further evidence about the core. The presence of a magnetic field is a clue that part of Earth's core must be a liquid metal. Convection currents stir the liquid, and it also rotates as Earth rotates. Because of these motions, and because it is a very good conductor of electricity, the liquid outer core generates a magnetic field through the dynamo effect, a different version of the process that creates the sun's magnetic field. From traces of magnetic field retained by rocks that formed long ago, geologists conclude that Earth's magnetic field has reversed itself in an irregular pattern, on average a few times per million years. Occasional reversals, though poorly understood, seem to be a characteristic of the dynamo effect. So speaking about this, so have you guys at least watched the movie The Core? Great. Luckily, so in the last 2 years in this course, the majority of the class haven't watched the movie The Core. So if you haven't watched The Core, please go watch The Core. And that you guys also realize that the magnetic field has changed in the past. So north becomes south and south becomes north. Yes, the movie's name is The Core. So when's it due to change? Again, I have no idea because I'm not a geologist. But yes, we have records, especially in. So, one thing is rocks can take a snapshot of the magnetic field. So, by looking at different sediment layers in Earth's crust, we can actually see that the magnetic field has swapped around, and that is a feature of the dynamo effect. I'm not an expert on it, but we have evidence that has happened before and it will happen again. The paths of seismic waves in the mantle, the layer of dense rock that lies between the molten core and the crust, show that it is not molten, but it is not really solid either. Mantle materials behave like a plastic, material with the properties of a solid but capable of flowing under pressure. The asphalt used in paving roads is a common example of a plastic. It shatters if trucked with a sledgehammer, but it bends under the steady weight of a heavy truck. Just below Earth's crust, where the pressure is less than at great depths, the mantle is most plastic. Earth's crust is composed of low-density rock that floats on the mantle. The image of a rock floating may seem odd, but recall that the rock of the mantle is very dense. Also, just below the crust, the mantle rock tends to be highly plastic, so great sections of low-density crust do indeed float on a semi-liquid mantle, like great lily pads floating on a pond. The crust is thickest under the continents, up to 60 kilometers thick, and thinnest under the oceans, where it is only about 10 kilometers thick. Unlike the mantle, the crust is brittle and can break when it is stressed. The motion of the crust and the erosive action of water make Earth's crust highly active, and notice 3 important points and 6 new terms. Plate tectonics, the motion of crustal plates, produces much of the geological activity on Earth. Plates spreading apart can form rift valleys, or on the ocean floor, mid-ocean rises where molten rock solidifies to form basalts. A plate sliding into a subduction zone can trigger volcanism, and the collision of plates can produce folded mountain ranges. Chains of volcanoes, such as the Hawaiian Islands, can result when a plate moves horizontally across a hot spot. Secondly, notice how the continents on Earth's surface have moved and changed over periods of hundreds of millions of years. 100 million years is only 0.1 billion years, a 1/46th the age of Earth. So sections of Earth's crusts are in rapid motion from the perspective of geologic timescales. Thirdly, most of the geological features mountain ranges, the Grand Canyon, and even the familiar outline of the continents, are recent products of Earth's active surface. Earth's surface is constantly renewed. The oldest rocks on Earth, small crystals of the mineral zircon from Western Australia, are 4.4 billion years old. Most of the crust is much younger than that. Most of the mountains and valleys you see around you are no more than a few tens of millions of years old. You can see that Earth's dramatic geology is dominated by 2 processes. Heat rising from the interior drives plate tectonics. Just below the thin crust of solid rock lies a semi-molten layer with motions that can rip the crust to fragments, push the pieces about like rafts of wood on a pond, and sometimes crash them together to raise mountains ranges and grow continents. The second process modifying the crust is water. It falls as rain and snow and tears down mountains, erodes river valleys, and washes soil and rock into the sea. Tectonics builds up mountains and continents, and then erosion rips them down. You can tell the story of Earth without mentioning its atmosphere. Not only is it necessary for life, but it's also immediately related to the crust. It affects the surface through erosion by wind and water, and in turn, the chemistry of Earth's surface affects the composition of the atmosphere. A modern understanding of planet building is that Earth formed so rapidly that it was substantially heated by the impacts of infalling material, as well as by radioactive decay. So the young Earth would have been highly volcanically active. When a volcano erupts, 50 to 80% of the gas released is water vapor. The rest is mostly carbon dioxide, nitrogen, and small amounts of sulfur gases such as hydrogen sulfide. The rotten egg gas that you smell if you visit a geothermal pools and geysers such as those at Yellowstone National Park. If Earth's surface was molten as it formed, then outgassing would have been continuous, and Earth's original primary atmosphere would have been rich in water vapor, carbon dioxide, and nitrogen. Astronomers also have suspected that some of the abundant water on Earth arrived late in the planet's formation process as a bombardment of volatile-rich comets. Spectroscopic studies of comets reveal that some comets, such as Comet Hartley 2, which was visited in 2010 by the Deep Impact Probe, have ratios of deuterium to hydrogen matching the ratio in the water on Earth, while other comets do not. Details of the origin of Earth's atmosphere and oceans are yet to be fully understood, and are subjects of current research. The atmosphere you breathe now is a secondary atmosphere produced later in Earth's history by chemical reactions between the atmosphere, crustal rocks, and surface water, and by green plants producing oxygen. Carbon dioxide is easily soluble in water, which is why carbonated beverages are so easy to manufacture. So the early oceans began to absorb atmospheric carbon dioxide. Once in solution, the carbon dioxide reacted with dissolved substances in the seawater to form silicon dioxide, limestone, and other mineral sediments in the ocean floor, freeing the seawater to absorb more carbon dioxide. Thanks to those chemical reactions in the oceans, most of the carbon dioxide was transferred from Earth's atmosphere to the seafloor sediments. When Earth was young, its atmosphere had no free oxygen, that is, oxygen not combined with other elements. Oxygen is very reactive and quickly forms oxides in the soil or combines with iron and other substances dissolved in water. Only the action of plant life keeps a steady supply of oxygen in Earth's atmosphere via photosynthesis, which makes energy for plants by absorbing carbon dioxide and releasing oxygen. Beginning about 2 to 2.5 billion years ago, photosynthetic plants in the oceans had multiplied to the point where they made oxygen at a rate faster than chemical reactions could remove it from the atmosphere. After that time, atmospheric oxygen increased rapidly. So this topic will be discussed again in chapter 20. So it's a common misconception there is life on Earth because of oxygen. The truth exactly is the opposite. There is oxygen on Earth's atmosphere because of life. Most life forms on Earth do not need oxygen, except the minority of creatures that are animals, including us, and some are even poisoned by it. Once the atmosphere began to contain abundant ordinary oxygen, Earth's lower atmosphere became protected from solar ultraviolet radiation by an ozone layer about 15 to 30 kilometers above the surface. Ozone molecules are very good at absorbing ultraviolet photons. An ozone molecule consists of three oxygen atoms linked together. Before there was oxygen, the ozone layer could not form, and the sun's ultraviolet radiation was able to penetrate deep into the atmosphere and break up the weaker molecules such as water. The hydrogen from the water then escaped to space, and oxygen formed oxides in the crust. Earth's atmosphere could not reach its present stable composition until it was protected by an ozone layer, and that required oxygen. You can live on Earth's surface because of Earth's atmosphere, but modern civilization is altering Earth's atmosphere in at least two serious ways, by adding carbon dioxide and destroying the ozone. The concentration of carbon dioxide in Earth's atmosphere is important because carbon dioxide can trap heat in a process called the greenhouse effect. When sunlight shines through the glass roof of a greenhouse, it heats the benches and plants inside. The warmer interior radiates infrared radiation, but the glass is opaque to infrared. Warm air in a greenhouse cannot mix with cooler air outside, so heat is trapped within the greenhouse. And the temperature climbs until the glass itself grows warm enough to radiate heat away as fast as the sunlight enters. This is the same process that heats a car when it's parked in the sun with its windows rolled up. So here we can see the greenhouse effect. In image A, visual wavelength sunlight can enter a greenhouse and heat its contents, but a lower wavelength infrared radiation cannot get out. Then in image B, the same process can heat a planet's surface if its atmospheres contain greenhouse gases such as CO2. In an image C, the concentration of CO2 in Earth's atmosphere as measured in Antarctic ice cores remained roughly constant for thousands of years until the beginning of the Industrial Revolution around the year 1800. Since then, it has increased by more than 40%. Evidence from proportions of carbon isotopes and oxygen in the atmosphere proves that most of the added CO2 is the result of burning fossil fuels. Earth's atmosphere is transparent to sunlight, And when the ground absorbs sunlight, it grows warmer and radiates at infrared wavelengths. However, CO2 makes the atmospheres less transparent to infrared radiation. So infrared radiation from the warm surface is absorbed by the atmosphere and cannot escape back into space. That traps heat and makes Earth warmer. CO2 is not only greenhouse gas. Water vapor, methane, and other gases also help warm Earth, but CO2 is the most important. It is a common misconception that greenhouse effect is only bad. Evidence indicates that Earth has had a greenhouse effect for its entire history. Without a greenhouse effect, Earth presently would be at least 30 degrees colder and uninhabitable for most living things, including humans. So something interesting for you guys. Have you ever thought why the average temperature at coastal regions are warmer than the interiors? So for example, if you take, for example, coastal regions, say for example, Cape Town, if you look at the minimum temperature is much higher. We usually 14, 15 degrees, even a bit warmer, and the daytime temperature is much closer to that. But going into interiors such as Gauteng, we can actually see that the minimum temperature is much lower and the day temperature is also further apart. You guys have any idea why that is? So yes, more water vapor in the air and more air above you, increasing pressure. Yes, it has a little influence. And yes, Miss Kutsia, you are correct. It's to do with the ocean's temperature doesn't vary that much. So yes, it's to do with the oceans. So Earth, so our ground, is not a very good thermal isolator. So it gets warmed up when the sun shines on it. But as soon as the sun doesn't shine on it anymore, it radiates its energy away very, very fast and doesn't retain that heat energy. But water, on the other hand, retains that energy. So water remains a lot warmer than the ground. So that's why the minimum temperature around the sea or coastal areas is much higher than internal areas and such as Gauteng. And that also means that the temperatures around coastal regions are a bit more stable than the interior of countries. So that's just something to ponder about. And have you guys always also noticed if you are at the ocean, at the sea, or at a beach, usually just before sunrise and usually just after sunset, 90% of the time, that would be wind still. Do you guys have any idea why? So it's wind still during those times because the ocean temperature and the air temperature above land are almost the same. So that means you don't have any high and low pressure systems, meaning you have no wind. But as soon as the ground gets warmer than the ocean, that means your atmosphere above the ground is warmer than the atmosphere above the ocean, meaning now you have different pressure systems, and that's why the wind starts blowing after sunrise and so before sunrise or around about sunrise to the sea, you'll see it's wind still, but as soon as the sun's a bit higher, then the wind will start blowing. And that is just something interesting for you guys. For 4 billion years, natural processes on Earth has removed CO2 from the atmosphere and buried the carbon in the forms of limestone, coal, oil, and natural gas. Since the beginning of the Industrial Revolution in the late 18th century, humans have been digging up lots of carbon-rich fields, burning them to get energy and releasing CO2 back into the atmosphere more rapidly than it can be naturally removed, thereby increasing the intensity of the greenhouse effect. Increased concentration of CO2 is increasing the greenhouse effect and warming Earth on what is known as global warming. And that is why it's important that we start moving away from coal. So that is why I said at the beginning of this module, I'm for nuclear energy. Nuclear energy is probably the most cleanest form of energy that we have. And I'm also for the use of electric vehicles. So when people don't realize is they say, oh, but what about load shedding? Load shedding won't influence your electric vehicle at all. Because not everyone, so not all 56 million people in South Africa charge, if there will be electric vehicles, will charge them at the same time. So load shedding is a misconception that will influence electric vehicles. And then secondly, there's a company that's installing charging stations across South Africa. There's now been deals with some of the major petrol brands that has to be electric charging stations at their petrol stations as well. So yes, that is a possibility. And I said if Tesla will come to South Africa, I'll probably be one of the first people to buy myself a Tesla. What about hydrogen? Hydrogen is also a good fuel source, but hydrogen technology still needs to improve a lot. But yes, that is also a very good option. But for us in South Africa, it would be nuclear power will be the best option currently. So the Model S plate, that would be very, very fun. But I will be happy even with a Model 3. So the problem is why Tesla is not in South Africa because our governments are greedy bastards. So Elon Musk wanted to open up the first Tesla dealership back in 2017 in South Africa already. But the problem is the government asks 50%, 56% import tax on electric vehicles. So that is why Elon Musk said he's not going to bring Tesla to South Africa yet because the import tax is too high. So if you think about it, if you do buy a Tesla in the US, the entry level Tesla you can buy for around about 400,000 Rand. So that is quite affordable. Your top of the range Teslas is around about 800,000 Rand. So for 400,000 Rand, that's the price of a new Toyota Corolla. And for that price, you can buy yourself a Tesla. But due to South Africa's greedy government and greedy import tax, that is now 50% tax on it. So that means you can almost double the price due to tax. So that's why the entry level cost in South Africa of Tesla will cost around about 800,000 Rand or even a million. But that is due to the damn tax on it. So Elon Musk said he would be bring it to South Africa if the import taxes is lower. So not buying a Tesla would be a very smart move in Israel, especially if you never leave your city or province. So maybe things will change now that he is the richest person also. Hopefully that will change. And that is something coming up. And if you look at battery technologies, there are new battery technologies. There's some car manufacturers. Who was it? I think it was Jag's new electric vehicle. I think they can get now 1,000 kilometers on one charge. So that is coming up. So I'm totally for electric vehicles. So it is a common misconception that human output of CO2 is minor compared to the natural sources such as volcanoes. Careful measurements of carbon isotopes ratios and relative amounts of CO2 versus O2 in the atmosphere show that the CO2 added to the atmosphere since the last atmosphere since the year 1800 or the 1800s is mostly entirely due to human burning fossil fuels. Estimates are that the amount of CO2 in the Earth's atmosphere could double during the 21st century. Studies of, excuse me guys, be with you in one. Sorry about that, I just had to take a sip of water. So studies of the growth of rings in very old trees showed that the average Earth climate had been cooling for most of the last 1,000 years. By the 20th century, revisited that trend with a rise of 0.56 to 0.92, so almost Celsius. Mountain glaciers have melted back dramatically since the 19th century. Measurements showed that polar ice in the form of permafrost, ice shelves, and ice on the open Arctic Ocean is melting. So, Ms. Garcia, you are saying we need to seriously implement renewable energy, but that's another problem for our government. Yes, that is true. And I don't know if you guys seen the last 5 years, we can actually see the effect of global warming around us. So recently, thinking about the floods in KZN. So the two contributing factors to the floods is firstly, number one, we are in an El Nino effect that is abnormal rainfall. Then secondly, is global warming. Due to global warming, climates are changing, and we will start seeing more extreme weather cycles. So that we will see more heat waves. If it's raining, we will see a lot more water, and that's due to global warming. So let's see, Mr. Pretorius is say import duties on passenger cars and light commercial vehicle bakkies are 25% ad valorem, which is low compared to other emerging markets where import duties can go as high as 100%. Even the US, a large development market, the import duty on light commercial vehicles, which makes up about 70% of the market, is 25%. Our duty on EVs is 25%, our tariff is not 50%. So that was the one thing. So yes, it's 25%, but I know the government said they are specifically going to tax Tesla with 56%. Don't know why, but there was a big fight about it. Yet another common misconception is that the observed warming on the Earth is due to natural causes rather than a greenhouse effect. As scientists began to study early indications that Earth's global climate is warming and that humans produced CO2 might be a major cause, they reacted with professional skepticism. They asked questions such as, is global warming really happening? And if the warming is real, is some mechanisms other than human activity the main cause? Experiments were conducted, calculations performed, and models created to answer those types of questions. Such research carried out over decades revealed that regular and predictable changes in Earth's axis inclined an orientation in the shape of its orbit, called the Milankovitch cycles. Currently, would have driven Earth's climate towards lower, not higher temperatures. Also, observations by space probes indicate that the sun's luminosity, average over its activity cycles, has been constant for decades or has decreased slightly. The observed warming must be strong to be occurring in the face of opposing astronomical effects. So, ladies and gentlemen, I see our time is up. So we will continue with this lecture on next week, and then we will also shift to the other rocky planets, Mercury, Venus, and Mars. So I hope that you enjoyed this lecture. So I know you said you guys are writing tests this week. So if you're writing tests, good luck with the tests, good luck with preparation of tests. I know it will go well. Then have a wonderful evening. I'll remain active for a minute or two if you have more questions. Otherwise, you're more than welcome to log off, and I will see you all next week. So far, I'm not planning to be on campus the rest of the week, but if you want me to be on campus, I can make a plan. Otherwise, we can set up a virtual meeting. Just please send me an email and we can organize something. So yes, the quiz is due before tomorrow midnight. You have 2 attempts to the quiz, and the best mark after 2 will count towards your final grade. It's a pleasure. So if there are no further questions, then I'm also going to log off. So have a great evening, everyone, and see you all next week.